Okay, so ready to dive into something really cool today. I'm talking next level stuff in the world of metal fabrication.
It's always exciting to explore the cutting edge, and what we're discussing today definitely fits the bill.
We're diving into the world of wire and Joule additive manufacturing.
Or WJM, as the cool kids call it.
Right, catchy, right. But more than just a cool name, this is a technology with some serious potential to shake things up.
It really does challenge a lot of the assumptions about what's possible with metal 3D printing, especially when we're talking about building complex parts.
And that's precisely what we're digging into today. We've got a fascinating research paper that lays out a brand new approach called continuous directional deformation deposition.
C3D, it's a mouthful.
Definitely easier to say WJ. But names aside, this paper, it's packed with these aha moments that really make you rethink what the future of manufacturing could look like.
It does an excellent job of highlighting those key bottlenecks that have kind of held back metal 3D printing, and then it just lays out this elegant solution that seems almost obvious in retrospect.
Okay, so no more holding back, right? Let's get to the good stuff.
Right.
What's the secret sauce? What makes WJM so different from everything else out there?
Imagine this. You need to create an incredibly intricate metal part. Traditionally, you're looking at these slow, expensive processes, carefully machining away material to get the exact shape you need.
Right, it's like sculpting with a block of metal, painstaking and time-consuming.
Precisely. Then along came 3D printing, and suddenly we could build these complex shapes layer by layer using lasers to melt metal powder.
Which was revolutionary in its own right.
Oh, absolutely. But even with 3D printing, there are limitations. It can still be slow. The materials you can use are somewhat restricted, and there are design constraints you have to work within. WJM throws a lot of those limitations out the window.
Okay, I'm intrigued. Give me the rundown. How does WJM actually work?
Instead of using metal powder like traditional metal 3D printing, WJM uses metal wire.
Metal wire. Interesting. So like a super precise, high-tech, hot glue gun for metal.
That's a great analogy. But here's where it gets really interesting. WJM uses two heat sources to achieve incredibly fine control over the process.
Two heat sources. Okay, now we're talking.
You've got Joule heating, which is essentially passing an electrical current through the wire to melt it. And then, and this is the really ingenious part, they add a secondary laser-focused heat source. But it's not for melting the wire directly.
Wait, what? If the laser's not melting the wire, what's it doing?
Think of it like an artist prepping their canvas. This secondary heat source is all about precision. It preheats the surface that the wire is being deposited onto, giving you incredible control over how that molten metal behaves.
So you've got one heat source melting the wire and another one preheating the surface it's being laid down on. That's brilliant.
It's all about control, right? And the paper uses this fantastic analogy. They talk about how WJM is like having independent control over both the ink and the paper at the same time. You can fine-tune the melting point of the wire, the viscosity of the molten pool, how it interacts with the build surface, all sorts of cool stuff.
That's incredible. It's like having this newfound level of control that just wasn't possible before with other methods. Okay, I'm definitely starting to see why this is such a big deal. But let's talk practicalities for a second. We've thrown around words like faster and cheaper, but in the world of manufacturing, those are bold claims. Give me some specifics. Just how much faster are we talking about here?
Hold on to your hat, because we're talking about speeds that would make your head spin. I mean, this paper cited a deposition rate, so that's how much metal you can lay down per hour, of almost 5 kilograms per hour for a common stainless steel. To put that in perspective, that's like 10 times faster than some existing methods.
10 times. Okay, now you're speaking my language. That's not just an improvement, that's a complete game changer. But you mentioned earlier that WJM can handle a wider range of metals too, right?
Absolutely. One of the limitations of traditional metal 3D printing is that it can be pretty picky about the materials it can use. But WJM, it's like the Wild West out there. You want to print with titanium alloys? No problem. How about super alloys, those exotic metals they use in rocket engines? WJM can handle it.
So not only are we building things faster, but we're building things we could barely even dream of before. It's like something out of Star Trek. What's next? Printing a starship in our backyard.
Hey, a scientist can dream, right? But in all seriousness, this technology opens up a world of possibilities for industries that rely on high-performance materials. I mean, think about aerospace, automotive, even medical devices.
It's incredible to think about the potential here. But let's address the elephant in the room. All of this sounds amazing, but new technology usually comes with a hefty price tag. Is WGM really as cost-effective as it claims to be?
It really boils down to a few key factors. Remember how WJM uses wire instead of powder?
Yeah, that super precise, high-tech hot glue gun we were talking about earlier.
Exactly. Well, wire is significantly cheaper than those fancy metal powders used in other metal 3D printing methods. And because that secondary heat source is doing some of the heavy lifting, you can get away with using a less powerful and therefore less expensive laser system.
So we're talking about a win-win situation here. Faster production, a wider range of materials, and potentially significant cost savings. But there was one more thing that really caught my attention. The ability to actually change the properties of the metal during printing. How does that even work?
That's where things get really interesting. It all comes down to the way WGM uses electricity to melt the wire. By carefully controlling the amount of electrical current, what we call current density, you can actually fine-tune the properties of the metal as it's being printed.
Wait, hold on. So you're saying we can manipulate metal with electricity now, like it's some kind of superpower. Tell me more. How does that actually work?
Imagine it like this. As the metal wire is being melted and deposited, we're essentially focusing this precise beam of electrical energy to shape its internal structure. We can enhance its strength, flexibility, resistance to wear and tear. It's really quite remarkable.
So not only can we print things faster, cheaper, and with a wider range of metals, but we can actually enhance the materials themselves during the printing process. Mind officially blown. But this has all been theoretical so far, right? We're talking about a research paper here. Have they actually built one of these things?
They have. The researchers behind this paper weren't content with just theory. They went ahead and built a WAM system to put their ideas to the test.
Okay, now I'm really excited. What kind of cool things did they print?
They printed all sorts of things. The paper shows images of a stainless steel cup, these incredibly complex lattice structures. But the one that really caught my eye was a mold with internal cooling channels.
Internal cooling channels. Now that's just showing off. I can't even imagine how you'd make something like that using traditional methods.
Exactly. It would be incredibly complex and expensive. But with WJJam, you can create these intricate internal geometries with ease. It's a perfect example of the kind of design freedom this technology unlocks.
We've talked about lasers being used as that secondary heat source, but if I remember correctly, that's not the only option, right?
You're absolutely right. The researchers also experimented with arc heating as an alternative to lasers for preheating the build surface. And the results were incredibly promising. This adaptability is another huge advantage of WJJam.
So it's not just limited to a lab setting. You could potentially take this technology on the road, use it to repair large metal structures in the field, all sorts of interesting applications.
Exactly. The possibilities are really quite exciting.
It sounds like WJM has the potential to completely rewrite the rules of manufacturing. But as with any emerging technology, I imagine there are still some kinks to work out. What are some of the challenges the researchers highlighted in the paper?
You're right. It's not all smooth sailing. One of the big ones they emphasize is the need for incredibly precise temperature control. We've talked about how WJM gives us control over both the ink and the paper, but getting that balance just right is critical. If the wire melts too quickly or the build surface isn't at the optimal temperature, you can end up with defects in the final part.
So there's a lot more to it than just feeding wire into a machine and hitting go.
Exactly. And it makes me wonder, how much of a learning curve is there for engineers and technicians who are used to working with traditional metal fabrication methods? It seems like a whole different way of thinking about manufacturing.
That's a great point. It'll be interesting to see how those traditional skill sets translate into this new world of WJM. But even with those challenges, the potential here is just undeniable. Faster, cheaper, more versatile, and even the ability to enhance materials at the atomic level, it's mind-blowing.
It really is. WJM has the potential to completely revolutionize how we approach manufacturing. I'm excited to see where this technology goes in the next decade, what new industries it unlocks, and what seemingly impossible creations it makes possible.
It's been fascinating to explore this groundbreaking technology with you today. To our listeners, if you're looking for a glimpse into the future of manufacturing, WJAM is definitely worth keeping your eye on. Thanks for joining us on this deep dive into the world of wire and Joule additive manufacturing.